Bismillahirrahmanirrahim. I welcome you all in the course of the heat and mass transfer. In the lecture number 13, especially the students of Khwaja Farid University of Engineering Information Technology, and of course all the engineering students can take the help from this. In the previous lecture, I have talked of the concentration boundary layer. The different numbers I have told you, that's Schmidt number, Shroud number, Lewis number, and we drive the concentration boundary layer with the analogy with the hydrodynamic boundary layer and the thermodynamic boundary layer. So today we will do the heat and mass transfer analogies, analogous form of the dimensionless boundary layer energy, and of course species equations that we have written and we have talked of in the previous lectures. So it follows that for a prescribed geometry and the equivalent boundary layer condition, the functional dependence of Nusselt and Schmidt numbers are: Nusselt number is a function of the position Reynolds number and the Prandtl number, and Shroud number is a function of x, that is the position Reynolds number and Schmidt number. As Prandtl number depends on the Nusselt number, and of course Schmidt number depends on the Shroud number. So in the case of heat transfer, Prandtl number and Nusselt numbers are going together; they are dependent. And in the case of the mass transfer, the Shroud number is a function of the Schmidt number, and they are mostly the power of n, the Prandtl number sum n on SC on n, whether it's an empirical relation or it's a derived equations. So its value is mostly varies from 0.3 to 0.4. So if I move to the Reynolds analogy, that for which we have already assumed that dp star by dx star is equal to 0, and for that case, of course, Nusselt number we have taken the Nusselt number in the case of the heat transfer is Cf Re by 2. This is the coefficient of friction, is the Reynolds number divided by 2, and of course Prandtl, in that case Prandtl number is equal to the Schmidt number, which is equal to 1. Therefore Nusselt number n is equal to the Shroud number, where we define a new number today, that is Stanton number, which is Shroud number, right, over Reynolds number into Schmidt number. This becomes Hm over V. Just put the values of the Shroud number, Reynolds number, and then the Schmidt number. You will get the Hm over V. Hm is of course the mass transfer coefficient. Mass transfer. This is called mass transfer Stanton number, STM. Mass transfer Stanton number. Stanton number we have also written for the heat transfer. So that is the ST. The STM is the mass transfer Stanton number. Hm is the mass transfer coefficient, convective mass coefficient, and V is the volume. So therefore modified Reynolds number is, so if I say the Cf by 2 here from Cf by 2 is equal to Stanton number m into Schmidt number 2 by 3, that is equal to Jm. This is the empirical relation for the Corbin factor for the mass transfer. We have also wrote the equation JH, that is the Corbin factor for heat transfer. This is for mass transfer. This is a Stanton number. STM means the mass transfer Stanton number, is Schmidt number is for 2 over 3, is Jm. It is the Corbin factor for mass transfer. It is applicable for laminar flow if and only if dp star by dx star is equal to 0, and it's applicable to transfer to turbulent flow without any restriction on the dp star by dx star rate, the gradient of the pressure along the x direction. So once it's a turbulent flow, you can use this equation for the Corbin factor for mass transfer without any restriction. But if it is a laminar flow, then if you have to consider whether it's a dp by dx star is 0 or not. The radiation of pressure along the x direction is 0 or not. The evaporative cooling. The term evaporative cooling basically originates from the association of the latent heat created by evaporation at the liquid interface with a reduction in the thermal energy of the liquid. So latent heat is the amount of heat required to convert a unit mass of any liquid into vapors. And it's a huge amount of energy, and of course when it's converted into vapor, it will reduce the temperature of that body, whether it may be a liquid or maybe anything. So if therefore evaporation always called cooling. So if evaporation occur in the absence of other energy transfer process, the thermal energy, and hence the temperature of the liquid must decrease. So if any other process are not to be taken place, then of course they take the energy from the body, and of course it will be it will cause cooling. For example, this is the liquid species A, and this is the gas flow over this, right? So this is the Q double dot, Q convective is coming in, Q evaporative is going out. When the gas flow over the liquid, of course it takes heat from the liquid and convert it into vapors, and at this layer of course some liquid is being evaporated. This is a gas liquid interface. At this interface, the molecules at the surface will gain a certain amount of heat or you can energy to escape from the liquid phase to the vapor phase, and that amount of energy is basically the latent heat. Evaporative cooling. So if you see in this case energy balance, the Q is convected, of course it Q is coming in, and Q heat evaporated is going out, and that is the Q added, right? Q added. So Q added is equal to Q convected plus the Q evaporated. So of course in this case what we are adding some heat, there is some heat from convection from the outside and some heat is evaporated. So Q added plus Q convected is equal to Q evaporated. So if the liquid is to be maintained at a fixed temperature, energy loss due to evaporation must be replenished by other means. So because in the whenever the phase change, of course the temperature constant. So if there's only evaporation will take place, the temperature will constant, and this energy is being replenished by some other means, right, from the atmosphere or any other case. Assuming convection heat transfer at the interface to provide the only means of energy inflow to the liquid. If you see in this case, of course, Q convected plus Q added is equal to Q evaporated. So double dash means it is per unit area. So Q double dash evaporated, of course, it is Na, right? That is the number of moles, right? Kilogram per meter square second, and HFG is a latent heat. And as far as this is the I'd say is the by convection, H T infinity minus Ts is equal to HFG multiplied by HM. HM is the convective mass transfer coefficient, which is rho A at saturated, Ts minus rho A at saturated minus rho A at infinity. That is the heat convected, and that is the heat evaporated. So I put HFG, right? HFG and A, and Na is equal to HM rho A at Ts minus rho A at infinity. So T infinity minus Ts is HFG HM by H. HM by H is the change in temperature. T infinity minus Ts. HFG HM by H, if we take downward, it is rho of species A at saturated temperature, rho of species A at the, of course, the free stream position, free stream condition, that is infinity environment. So left hand term is the steady state cooling, and right hand term is the obtained by heat and mass transfer analogy. This is the heat transfer, of course. This is the left is a steady state cooling, its temperature is coming down, and the right side is basically is obtained by heat and mass transfer energy. So heat convected plus heat added is equal to heat evaporated. Heat evaporated is the amount, HFG amount, the number of moles per number of kilograms per meter square per second. So that, of course, and A, we know that it is basically by means of the convective mass transfer coefficient. HM, it is the density of species A at a particular saturated temperature of surface temperature minus the, of course, the density of A at the environmental temperature. So from here we can find the change in temperature based on this, right? Is the function of HFG, that is basically the latent heat of that particular species, and that is the HM is the mass transfer coefficient, and H is the convective heat transfer coefficient. So, dear students, you see that the convective mass transfer coefficient and the convective heat transfer coefficient are being related also in the case of evaporation, and you can find out from here. So let's do the examples. A long circular cylinder, 20 mm in diameter, is fabricated from solid naphthalene. A common moth repellent is exposed to an air stream that provides for an average convection mass transfer coefficient of H bar m is 0.05 meter per second. The molar concentration of naphthalene vapor at the cylinder surface is 5 × 6 kilomole per meter cube, and the molecular weight is 128 kilogram per kilomole. That is the molecular weight of that species which is being sprayed. So what is the mass sublimation rate per unit length of the cylinder? So this is the cylinder. Its diameter is 20 millimeter. This Ca that is given to you here, that is the 5 × 6 kilomole. The molar concentration of naphthalene is 5 × 6 kilomole per meter cube, and that is the long length. Of course, Ca infinity, that is the concentration of air, is of course 0, and the mass transfer coefficient is 0.05 meter per second square. This is air. A species is air, and B species is the naphthalene. It is just basically naphthalene. Naphthalene is basically a sublimate, and you open a moth. Moth means moth repellent is just a spray just we use for the killing of the insects. So due to this, what is the mass of sublimated per unit length of this cylinder? So it's a mass transfer problem. So diameter is 20 millimeter. H bar m is 0.05 meter per second. These are given to us. Cax, which is basically given to you the concentration coefficient, that is 5 × 5 kilomole per meter cube, and at infinity it is 0. Length is long, and molecular mass of that particular thing is 128 kilogram per mole. This is the molecular mass of a weight is of the naphthalene. Okay. Mass sublimated rate per unit length is Na, is kilogram per second per meter. That is Na we need to find. So according to the mass transfer equation that we have already written, Na is equal to H bar m As surface area Cs minus Ca infinity, and Na dash, let's say Na dash is basically, this is per unit, this is along the area. If I want to take per unit area as Na by L, so Na dash H bar m, and if it's a cylinder, so pi d times L, so it is pi d L. We divide with the L because we need to find this amount, that is in kilogram per second per meter, not per unit area. So therefore I divide with length, so pi d, and the concentration at S minus concentration coefficient at infinity. Na dash is equal to H bar m pi d, as Ca infinity is 0, Cas. So I know the value of pi, diameter, H bar, and the Cas. That is the concentration, right? This is the value of Ca, right? That is the molar concentration. We know, we might just put the value here, and we get Na dash 1.57 exponent minus 8 kilomole. That is kilomole per second per meter. So we need to find in kilogram per second per meter. So as we know that number of moles is equal to mass per unit mole, molecular mass. So just multiply with this molecular mass, which is basically given to you 128. It becomes 2.01 exponent minus 6 kilogram per second per meter. So in this case, 2.01 exponent minus 6 kilograms. Right? You can say 2.01 exponent minus 3 gram, or you can say 2.01 milligram per second per meter is being evaporated. Let's see the next example. At some location on the surface of a pan of water, measurements of the partial pressure of water vapor, the atmosphere, are made as a function of the distance y from the surface, and the results are plotted. This is the atmospheric pressure, and this is at the y. As you see, the atmospheric pressure is low at y, that is high pressure. At a larger value of y, the pressure is low. As you are moving forward, the pressure is increasing. The question is, determine the convection mass transfer coefficient at this location. Okay, the saturated vapor, if you see, the saturated vapor is at about 0.1 atmosphere. At 0.1 atmosphere, the vapors are being saturated, completely saturated, as the graph shows, because there is no that y is equal to 0 here, right? So that is 0.1 atmosphere, 0.101 bar, and the TS is 319 K. From table, you go to the tables at the appendix A6. So from table A, so water vapor and air is 319 K. We can find out the value of DAB, boundary coefficient. binary species coefficient DAB at 319. It is basically pressure 1 raised to power minus 1 is 1 atmosphere. So it is the temperature 319 over 298. Because it is given 298, we need to find at 319 raised to power 3 by 2. This is given in the appendix A. So I can find the value of a DAB from here. So as we know, the diffusivity coefficient for the binary mixture of the gases may be DAB is the equal to P minus 1 T raised to power minus 3 is a 3 by 2. So from this equation, I find the value. So DAB 319 minus 1 319 by 2 883 by 2 multiplied by DAB 298. This value is given in the table, and this factor is to be multiplied if the temperature is different. It is a pressure raised to power minus 1, the temperature at which we are taking the DAB, that is basically the binary diffusion coefficient, or this 298 the standard temperature is 25 degrees Celsius. So we can find the value of this is basically 0.288 10 to the minus 4 meters square per second at 319 K. So now we can find the local convection mass transfer coefficient by using this very simple equation we have done in the previous lecture. HM and X minus DAB curly PA by curly PA by curly Y at Y is equal to 0. That is the PAX minus PA infinity, or approximately vapors are as an ideal gas. So PA is equal to rho ART with constant T. So HM is equal to minus DAB curly PA by curly Y at Y is equal to 0 PAX minus PA infinity. From the measured vapor pressure distribution, which is given to you, dPA by dy, if you see here, it is 0, right, and 0.1, 0 minus 0.1 divided by 0.003, right, this is 0.003 minus 0, right. So that is the change in pressure over change in Y. If you see this is the 0, right, and that is 0.1 is the change in pressure. And what is the change in the Y? Y is basically from 0.003 to 0. 0.003 from here, right, from 0.030 to 0, because this is saturated where the graph becomes in the downward direction. So that is minus 0.1 to 0.03 is minus 33.3 atmosphere per meter. There is a change in pressure per meter of length, right. So if we know this value, right, we can put it here, and we know that dPA and all these values are given, we can find the convective heat transfer coefficient. Okay, let's move to the problem 6-64 in your book. Consider application of the naphthalene sublimation technique, that is problem 6.63, to a gas turbine blade that is coated with the naphthalene and has a surface area of 0.05 meters square. To determine the average convection heat transfer coefficient for the representative operating condition, an experiment is performed in which the coated blade is exposed for 30 minutes to atmosphere air at the desired velocity and a temperature 1850-27 degrees centigrade. During the experiment, the surface temperature is 27 degrees centigrade, and at its conclusion, the mass of the blade is reduced by 8 grams. That is, the 8 gram is the amount which is being sublimated. What is the average convection heat transfer coefficient associated with the operating conditions? So this is the blade, of course, and air is flowing, right, with the velocity v, and of course temperature is infinity. The turbine blade is coated with the naphthalene. Of course, surface area is AS, TS, and we have given the P saturated at TS. That is the rho, the density at the saturated temperature. So we are given the P infinity, atmospheric temperature, atmospheric pressure, 1 atmosphere, the atmospheric temperature 27 degrees centigrade, surface temperature 27 degrees centigrade, of course, not given. It means the surface and the environment are at same temperature. The surface area is given to you 0.05 meters square, and of course we are given the saturated pressure is 1.33 x to minus 4 bar. Delta which is being evaporated is 8 gram. In how much time is that? 30 minutes. So the assumptions that we made for solving this problem: heat and mass transfer analogy is applicable. AS is constant, no change due to the mass loss. Naphthalene means surface area. Naphthalene vapors behave like an ideal gas. And we also, the solid vapor are in equilibrium at surface coating, and they are equal rate of rate of conversion, solid to vapor, vapor to solid, it is a saturated state. Negligible variable density in free stream of air flow. So we are taking the density of the air is constant. So properties are we evaluated from the air table, because it is species A is air. From table A4 I read the different values. At the 300 K the density is 1.61 kilogram per meter cube. The value of Cp 1.007 joule per kilogram Kelvin. Alpha, the diffusivity, is 22.5 at 10 to the minus 5 diffusion coefficient meter square per second. Naphthalene vapor air. Naphthalene vapor and air for naphthalene and vapor air when species A and B are this. Then at 300 degrees centigrade, the Barney diffusion coefficient, that is Barney diffusion coefficient, that is DAB, is 0.6 10 to the minus 5 meter square per second. The average mass transfer coefficient is, as we know, that Na is equal to H bar M AS, rho AS, rho of species A at surface minus rho species of A at the infinity. So from here I can find H bar M. As the number of moles, we can find out the mass transfer per unit time is with delta M by delta T, right? So it is delta M by delta T, AS, rho AS, and this is basically 0. We are given it is equal to 0. So we have the value for H bar M. Now we calculate density of naphthalene at saturated temperature. So PV is equal to MRT, PV is equal to rho RT, and rho is equal to P over RT, or rho is equal to PMART. So it is the pressure is 1.33 x to 1.4 saturated pressure. The molecular mass is 128.6. The value of R is 8.314 divided by 1000, right? Why I divide by 1000? Because this value should be converted into kilojoules, multiplied by 300. So that is the temperature. So the density is 6.883 exponent minus 4 kilogram per meter cube. So I put this value, I know the change in mass, temperature, the time, the surface area, the density is known. I put all the values, I get H bar M is 0.13 meter per second. This is the convective mass transfer coefficient. Now we have the relationship for the convective mass transfer coefficient and the convective heat transfer coefficient is H bar over HM is rho Cp, the Lewis number 2 raised to power 3, which is also equal to H bar M rho Cp Le 2 by 3 if you want it. H bar, I know the value of H bar is 1.16, which I find out here. 1.16 is the value of the density, I think so. So yes, value of the density is this much. So 0.13 is a Cp is the 1007. This is 0.13, that is density, and this is the Lewis number is alpha over DAB. We know the value of alpha, we know the value of DAB, we get put it here. So what is 1.16, which we put here, that is the density of air. Of course, the density of air convection. Here we take the density of air. This is density of air. So 1.16 and 0.13 is the HM, of course, and that is Cp value of air. And then remember that we take the value of A, which is basically air, and alpha is also read from the table A4, and we can find the value of H bar is 359 watt per meter square Kelvin. So the convective heat transfer coefficient is 359 watt per meter square Kelvin, and the mass transfer coefficient is only 0.13 meters per second. Let's go to the problem 6-58. Consider conditions for which a fluid with a free stream velocity v 1 meter per second flow over an evaporating or sublimating surface with a characteristic length of 1 meter, providing an average mass transfer coefficient of H bar M is equal to 10 to the minus 2 meter per second. Calculate the dimensionless parameter, the Sherwood number, Reynolds number, Schmidt number, and the mass component factor for the following combinations: airflow over water, airflow over naphthalene, and warm glycerol over ice. Assume a fluid temperature of 300 Kelvin and a pressure of 1 atmosphere. I selected this problem because you should, in this question, you will clear which is the species A, which is the species B, and for which species we are using the different values of the properties. So first we have air, and first of all air or glycerol, of course, is flowing at temperature 300 K and velocity is 1 meter per second. and this the other is the water, naphthalene, and or water in liquid water in vapors, or naphthalene vapor and water in vapor. Length is 1 meter. The convective mass transfer coefficient is 10 to the minus 2 meter per second. Temperature is 300 K, velocity is 1 meter per second, length is 1 meter, pressure is 1 atmosphere. We need to find Shroud number, Reynolds number, Schmidt number, and Copeland factor. First, the three conditions: airflow over the water, airflow over naphthalene, warm glycerol over ice, right? These are the conditions that we will discuss. So, first of all, we read the properties of the fluid. Is a table. If you see which table I'm using, I'm telling you fluids. I need the kinematic viscosity and DAB binary diffusion coefficient. So for air, from table A4, I read the value of the kinematic viscosity. From A5, I read the value of kinematic viscosity for glycerine. But when the interaction rate takes place, water vapor and air, then I read the value of DAB, 0.26 exponent minus 4, right? Then of course we go to the water vapor. For naphthalene, air, we go to naphthalene table, 0.62 exponent minus 5 meter square per second, and for water and glycerol, we go for this, of course, for water, that is 0.94 exponent minus 9. For glycerol, right? So water vapor, air. Okay, condition Shroud number is h bar m L DAB. I put the value h bar m, length is 1, and DAB we have read out is 385. Reynolds number rho VL upon nu is very simple. Put the value, you get this. Schmidt number is nu or DAB, and DAB we use the DAB of between the water vapor and air. Water vapor and air is this one, 0.26 exponent minus 4. We get the value of 0.6, and the Copeland factor is STM SC 2 by 3. It is basically HM by V. V is the velocity, and Schmidt number 2 by 3, 0.01 by 1. That is 0.62 to the power 3, 0.0073. Now if we go for naphthalene vapor and air, then of course Schmidt number, we use the h bar m given to us, 0.01, length is 1, DAB, the corresponding DAB of naphthalene and air which we have read from the table, and that is shown here is 0.62, right? I put it here. Reynolds numbers, rho VL upon A, and the Schmidt number, of course we put the values, we get the value of the Schmidt number. Now the Copeland factor, Copeland mass factor, Copeland factor for mass transfer, that is STM, Schmidt number, HM by V, 2.6 raised to power 2 by 3, I get the value of 76.9. Now let's we go for the water, liquid, and glycerol. For this case, Schmidt h bar ml, we have the h bar 0.01 L, and DAB is of course of the glycerol, right? So it is 1.06 exponent 7, and Reynolds number is rho VL by L, no problem. And Schmidt number is of course nu over DAB. We know the value of nu in this. We put it here. This nu is basically sorry, for glycerol, and the Copeland factor for mass transfer is HM by V. We find the value of 76.9. So remember that nu is for the free stream fluid B. The free stream fluid B, we are finding the nu, right? And as for a DAB, we are finding the DAB for the two interaction surfaces, which is given in the tables. So dear students, this completes the chapter number 6. In the chapter number 6, we have discussed the concept of, first of all, the velocity boundary layer, the thermal boundary layer, and then the concentration boundary layer. Then we talk of the interaction between the velocity boundary layer and thermal boundary layer, and then we also talk of the interaction between the velocity boundary layer and the concentration boundary layer and the thermal boundary layer. And I have solved some of the examples and problems, and I hope you like this. If you like, please like this video, and I hope this will help you. And my next lecture from the chapter number 7, which is the flow over the open surfaces. We talk of the flow over the flat plate for the laminar flow, and then the flow over the flat plate over the turbulent flow. And then the chapter number 8, the flow in the closed channels, right, for the conduit, like from pipes and rectangles. I hope you will learn from this, and please like it. Thank you.